Hello everyone, my name is Ajay Meddi from Aeronautical Engineering. In this presentation, I am going to discuss about nanofluids and their properties. Abstract. Nanofluid is a mixture of small concentration of nanometer sized solid particles like nanoparticles, nanotubes or nanowires suspended in the liquid and making a colloidal suspension. It is relatively a new field of which is less than 2 decades old. Nanofluid attracts researchers in many ways for their enhanced heat transfer properties. Nanofluid has better heat transfer performance than the base fluid. This presentation represents a comprehensive review on the preparation and stability of nanofluid, maintaining stability, evaluating stability, etc., and different thermal physical properties like convective heat transfer coefficient for laminar and turbulent region, thermal conductivity, specific heat capacity, viscosity, etc., and some transport phenomena like pool boiling heat transfer, flow boiling heat transfer. Introduction. Nanofluids are an innovative heat transfer fluid and have been in research over the past 2 decades. Their heat transfer augmentation is mainly due to small concentration of nanoparticles that dramatically change or enhance the thermophysical properties of the base fluid. These nanofluids are comprised of a base liquid such as water, ethylene glycol, propylene glycol or oil, and a small volume fraction of small some metal oxide or ceramic, as well as other materials with particle size ranging from 1 to 100 nanometer. Popular particles include chemically stable metals, that is silver, aluminum and copper, metal oxides or carbon, etc. Most suspensions contains less than 4% by weight or volume of the nanoparticle. The term nanofluid, first coined by Choi in 1995, show promise of enhancing heat transfer characteristics in applications such as electronics cooling, nuclear reactors and engine cooling, as well as solar energy applications. As today's system become increasingly complex with decreasing size, adequate cooling systems become more critical. Nanofluids can supplement the heat transfer capabilities of the base fluids, potentially lead to reduction in energy consumptions. Preparation of nanofluid. Preparation of nanofluid is very important factor as it determines its stability. Preparation of nanofluid is the first step in experimental studies of nanofluid. Nanofluids are primarily prepared using two methods: two-step method and one-step or single-step method. Two-step method. Two-step method, four processes is required in the preparation of nanofluid, namely drying, storage, transportation, and dispersion are done only in two steps. Firstly, nanoparticles, nanofibers, nanotubes, and other nanomaterials are produced as dry powders, neither by using chemical, physical methods or commercially available nanopowder, and then agitating the mixture using an ultrasonic vibrator or high shear homogenizer, etc. Two-step method is economical as large-scale production of nanofluid are possible because nanopower synthesis techniques have already been done in industries. This method is not capable of producing a very stable nanofluid which affects the thermophysical properties of nanofluid. Wang observed that as compared to the single step method, the two step method works well for oxide. Next, one step method, it is a process of nanofluid preparation where nanoparticle preparation and its dispersion are done simultaneously. One step method reduces the chance of nanoparticles agglomeration which leads to stable nanofluid, while this method has some disadvantages like it is applicable to only low vapor pressure fluids and the presence of residual reactants due to incomplete reaction or stabilization in the nanofluid. Nanoparticles effect is difficult to explain without removing these impurities. Out of these two methods, generally two-step method is used for the preparation of nanofluid compared to one-step method. Instead of having poor stability mainly due to ease of preparation produced in large scale. Thermophysical properties. Convective heat transfer coefficient. First one, laminar. Kelbasi et al. Found enhancement from AI203 and TI02, but determination for SiO2. They proposed that low thermal conductivity of SiO2 attributed these results, but the assumed Einstein equation for viscosity, even though nanofluid at high concentration behaves as non-Newtonian fluid and level of precipitation has not been checked after the experiment. Utomo et al. Found an insufficient change in Nusselt number due to AI203, TI02 and CNT. Here no uncertainty analysis was done in the experiment and no detailed temperature measurement procedure was provided. Harris et al. Found an increase of coefficient of convective heat transfer in nano non-circular duct with volume fraction and Reynolds number. Turbulent. G. et al. Reported critical Reynolds number RA 25 into 109, above which Nusselt number which be equal to the base fluid, but they did not specify the I value for the Reynolds numbers of no fluid. Thermal conductivity. Generally, low thermal conductivity of the heat transfer fluids is a primary limitation in many industrial applications. Maxwell theoretical studies suggested that dispersing solid in fluids enhance the thermal conductivity of the fluid, while its studies are confined to microparticles, which have issues like sedimentation and clogging, limits its application. Nanofluid having enhanced thermal conductivity than the conventional fluid resolves its limitation. Thermal conductivity of nanofluids is measured by employing different techniques like intrinsic hot wire method, thermal constant analyzer techniques, steady state parallel plate method, 3 omega method. There are different mechanisms for the enhancement of thermal conductivity discussed by several researchers experimentally or numerically, like Brownian motion of nanoparticles, liquid layering nanoparticle clustering, ballistic phenon transport of nanoparticles, thermophorics, near field radiation. Specific heat. There are some researchers proposed mechanics for the enhancement of specific heat capacity, like higher specific surface energy, increased interfacial thermal resistance between nanoparticles and surrounding liquid molecules, the formation of semi-solid liquid layers around the nanoparticles. Generally, specific heat capacity is measured using differential scanning calorimeter and modulated differential scanning calorimeter. Chinet L found that addition of the silica nanoparticles enhances the specific heat capacity of carbonate salt eutectic. They found that enhancement of specific heat capacity was larger for liquid phase than the solid phase. The enhancement is due to the formation of a compressed phase around the nanoparticle, which develops into a large needle shaped structure which form percolation network leads to enhancement in the specific heat capacity, in turn reduces the cost of thermal power by 50%. SheNet found 14.5% enhancement in specific heat capacity with 1% of mass concentration of SiO2 nanoparticles in alkali chlorides salts like BaCl2, NaCl, CaCl2 and NiCl with the measurement uncertainty 2% to 4%. They proposed three mechanisms for this enhancement specific heat capacity of nanoparticles due to higher specific surface energy than bulk material. Anomalous increase in interfacial thermal resistance between nanoparticles and surrounding liquid molecules due to extreme high specific surface area of the nanoparticle. Semi-solid liquid layer around the nanoparticles that reduces the intermolecular spacing and thus lowers the mean free path, enhancing the specific heat capacity. Thomas proposed that an absorption layer at the nanoparticle base fluid interface caused the specific heat capacity enhancement. Increased thickness of this observed layer yields greater enhancement in the specific heat capacity. Joe and Ni found that the specific heat capacity decreases with increasing nanoparticle volume concentration. However, they used the mixing rule to determine the mixture specific heat capacity. Furthermore, the stability of the nanofluid was not checked. Viscosity. Viscosity is a thermophysical property which plays an important role in application of nanofluid in the field of chemical and petroleum engineering. Viscosity affects the fluid efficiency in lubricating, pumping power, heat transfer and efficient oil production during enhanced oil recovery activities. The viscosity of water-based nanofluid has been studied by many researchers. Researchers worked on the dependency of nanoparticle viscosity on the nanoparticle volume, concentration, nanoparticle size, nanoparticle shape, temperature, the viscosity of base fluids. Most of the experiments were conducted on the water-based Al2O3, TiO2, Ci, SiO2 and CuO nanofluid. Pool boiling heat transfer. Boiling is a process of changing a liquid into vapor at a constant temperature. This change can takes place in number of phases depending on the way in which phase change takes place. Boiling is divided into two categories: pool boiling and flow boiling. You found that the addition of nanoparticles in fluid leads to enhancement on critical heat flux even at low particle concentration up to 0.01 gram per liter. Dash 8 observed that the pool boiling performance of the fluid deteriorated with the increasing volume fraction of the nanoparticle. Wu Elert reviewed that the critical heat flux enhancement of nanometer, the pool boiling heat transfer of pure liquid depends on both thermal properties of the nanofluid and other surface characteristics of the heat surface. Particle image velocimetry observed that in addition of nanoparticles, the hydrodynamic behavior changes. Nanoparticle deposition enhances CHF in boiling heat transfer. An and Kim received CHF enhancement in both pool boiling and flow boiling different experimental results and reported some consistent observations, that is, addition of nanoparticles enhances the CHF addition, adding 0.001 gram per liter Al2O3 particle with result in a slight increase in CHF with the increase in concentration of nanoparticles. The CHF will also increase when the concentration reaches 0.005 gram per liter. The CHF was enhanced by 200%. Conclusion. In this presentation, an overview of recent research programs in the preparation, stability, thermophysical properties and some transport phenomena like pool boiling heat transfer and flow boiling heat transfer of the nanofluids. Most of the experimental and numerical studies indicate that nanofluid have enhanced heat transfer coefficient compared with its base fluid. Stability is an important factor which determines the enhancement and deterioration of thermophysical properties of a nanofluids. Several researchers have observed enhancement in thermal conductivity of nanofluids. However, the hot wire method is mainly employed for measurement of thermal conductivity of nanofluid, leads to erroneous results. The enhancement of specific heat capacity of nanofluids due to an absorption layer around the nanoparticle is discussed. The enhancement specific heat capability shows promise in thermal energy storage applications. It is also found that the critical heat flux will increase for both pool and flow boiling for a small concentration of nanoparticles. The nanofluid changes the surface morphology which decreases the content angle and enhancing the critical heat flux. Viscosity is also an important parameter which determines the pressure drop and energy consumptions. While a very less number of papers deal with the viscosity of nanofluids, the behavior of nanofluids as Newtonian or non-Newtonian is highly debated. Several researchers agree that nanofluids having a low very low fraction of nanoparticles will behave as Newtonian fluids, and that with a higher volume fraction behaves as non-Newtonian fluid. Thanks for watching.